So good day, everyone. This is the new topic for Engineering Mechanics 2 under Curvilinear Motion of Particles, which will be talking about normal and tangential components. So just an introduction for the normal and tangential components. When we consider motion of a particle that is moving along a curved path, we have actually many procedures. It could be the first one we had discussed was um, rectangular components, and the second was motion of a projectile. So when the path along which a particle travels is known or given, then it is often convenient to describe the motion using n and t coordinate axis, which act normal, which is this is the n coordinate axis, and tangent, which is the t coordinate axis to the path. And at the instant considered have their origin located at the particle. So we have this illustration. So as you can see here in this illustration, the particle here is considered as the origin, and from the particle, it describes the n and t coordinate axis, which are the normal and tangent to the path of the particle. So we have also its position. So when we say its position, it describes from the fixed point, say the point O, and from point O going to the particle, that is the position of your particle. So the t-axis or the unit vector ut is tangent to the curve at the point and is positive in the direction of increasing s, while the normal axis n or the unit vector un is perpendicular to the t-axis with its positive sense directed toward the center of curvature O prime, which is always on the concave side of the curve. So generally, normal and tangent are perpendicular to each other. So it forms a 90 degrees. So again, we can actually use the normal and tangential components if ever the path of the particle is known or given. So the plane which contains the n and t axis is referred to as the embracing or osculating plane. And in this case, it is fixed in the plane of motion. So what we will discuss for the normal and tangential components is the same from the previous topics we had. We also discussed the geometric aspects of the particle that is moving along a curve. So we will discuss also the velocity and acceleration for considering the normal and tangential components. So let's talk about the velocity. Since the particle moves rather, s is a function of time, and the particle's velocity v has a direction that is always tangent to the path and a magnitude that is determined by taking the time derivative of the path function s, which is a function of time, and it is using the kinematic equation of v is equal to ds over dt. So what we always knew about velocity is that velocity is always tangent to the curve path. Hence, the first equation shown here is actually uh, the vector form of the velocity, and the vector form of the velocity is equal to the magnitude of the velocity, which is the italicized letter v, times the unit vector ut, which is the axis that is tangent to the curve, where the magnitude of the velocity can be found by taking the time derivative of the path function, which is the s. So s dot, meaning that we need to take its time derivative. So that is derivative of the path with respect to time. And as you can see here in this figure, the velocity is tangent to the curve. So the next is about the acceleration. So the acceleration of the particle is the time rate of change of the velocity. Thus, we have this formula. We got this formula from the uh, vector form of the velocity, which was the velocity vector is equal to its magnitude times the unit vector ut. So from this equation, we can use this to determine the acceleration of the particle. So it's by using the product rule, we get the equation for the acceleration. So just a basic definition of acceleration, it is the time rate of change of the velocity. So from that, the time derivative of the unit vector ut, or we have this the ut dot, this one, has its equivalent expression, and therefore the simplest form of the acceleration is equal to the at, or the tangential acceleration, times the unit vector ut plus the normal acceleration times the unit vector un, where um, the tangential acceleration is the time rate of change of the velocity, or the first derivative of the velocity, which is the v dot, or using the third kinematic equation, which is ATDS is equal to VdV. And the normal acceleration is equal to the v squared over the rho. Rho means the radius of curvature. And for the normal and tangential components, only the acceleration has both the normal and tangential components. Unlike with the velocity, it has only the tangential component. So as you can see here in the illustration, this is our particle, and considering the normal and tangential components as the um, normal and tangential components of the acceleration, which are the an and the at. And therefore, the magnitude of acceleration is the positive value of using this formula, which is a is equal to square root of at squared plus an squared. So the at and an, or the tangential and the normal accelerations, are the components of your acceleration. So we can actually determine the magnitude of acceleration by using the Pythagorean theorem. And the tangential component of acceleration represents the time rate of change in the magnitude of the velocity, while the normal component of acceleration, for the an, represents the time rate of change in the direction of the velocity. And since an, or the normal acceleration, always acts towards the center of curvature, this component is sometimes referred to as the centripetal or center-seeking acceleration. Because like what I've discussed earlier, the normal component is acting towards the center of curvature. And for this illustration, as you can see here in this illustration, every time the particle is moving along the curved path, um, there's always a change in its normal and tangential components. So, uh, considering an increasing speed, so at the first position, as you can see, um, we have here its normal and its tangential component. Next is for the second position, it changed or the normal and tangential components change. So here is the normal and it's tangential. And as it goes to the next position, if ever the curve is a straight line, so the acceleration is equal to the tangential acceleration. So basically, if you have a curved path, and this is your particle, the tangential axis or the tangential component is always tangent to the curve, which the particle is considered as your origin. And considering this e-axis, um, you will find here the velocity of the particle and also the tangential acceleration or the AT. For the normal, which is perpendicular to the tangential axis or the t-axis, what we have here is only the normal acceleration or AN, and it acts towards the center of curvature. So just a procedure for analysis, what we will do is first, we need to establish the coordinate system. So provided the path of the particle is known, we can establish a set of n and t coordinates having a fixed origin, which is coincident with the particle at the instant considered. And take note, the positive tangent axis acts in the direction of motion, and the positive normal axis is directed toward the path's center of curvature. So after we establish the coordinate system, we determine the velocity. The particle's velocity is always tangent to the path, so always take note on that. And the magnitude of the velocity is found from the time derivative of the path function, which is v is equal to s dot. So s is the path of the curve. So you just only determine the time derivative of the path function, which we can consider that as the magnitude of the velocity. And for the acceleration, like what I've mentioned, it has two components, the tangential and normal components. So first is for the tangential acceleration, it is the result of the time rate of change in the magnitude of velocity. And this component acts in the positive s direction or in the opposite direction if the speed is decreasing. So we can determine the tangential acceleration considering the relations between AT, V, T, and S are the same as for rectilinear motion, namely the tangential acceleration or AT can be found using the two equations. Would be finding by determining the first derivative of the velocity with respect to time. So that is AT is equal to V dot, or using the third kinematic equation, which is AT ds is equal to V dv. And if ever in the problem that the AT or the tangential acceleration is constant, we can actually use these three equations for us to determine the other needed uh, the other variables that we need to find in a certain problem. So using the equations here, when integrated, yields to this three equations. Actually, these three equations below, we actually use this in the topic of free falling bodies and also in the uh, motion of projectile. And lastly, for the normal acceleration, it is the result of the time rate of change in the direction of the velocity. And this component is always directed toward the center of curvature of the path, which is along the positive n-axis. And take note when we talk about positive n-axis, the um, axis itself is directed toward the center of curvature. And the magnitude of the normal acceleration can be determined from the following equation, which is an is equal to v squared over the rho. And if the path is expressed as y is equal to the function of x, we can actually determine the radius of curvature rho at any point on the path, which is determined from the equation given here. So if ever in a problem, there's no value for the radius of curvature or the rho given, so you can actually use this equation if ever the path is expressed as y is equal to the function of x. So after this one, we will have three example problems that is related to the normal and tangential components.